we've been talking about light and how it acts like wave and how it acts like particle. Well, Louis de Broglie is how you say his last name, said, well, if light can act as a wave or a particle, so matter should be able to as well. So he goes, okay, so if light, no, gotta get my pen back. Uh-oh, guys, my pen's not working. Hang on. Come on. Uh-oh. Hang on. Okay, Zoom is not agreeing with me. Talked about Bohr. Now we're going to talk about de Broglie because that's kind of like what came after the Bohr model, because we know that electrons don't actually go in circles around an atom. The next step in that was de Broglie, and he said, like I said, if light can act as a wave / particle, then what about matter? Okay, and this is kind of where we start getting into electrons, because we know electrons have a little bit of mass. And he had an equation for this. Now, this is not an equation that you guys will have to do a calculation with. I'm just going to show you what it is. And that's wavelength equals h, Planck's constant, over mass times velocity. So like this is how fast things move. So this is velocity and this is mass. So how big they are. So this can actually tell us like what the waves or the electrons, which are matter, what they're acting like, how they're moving. Are they moving in a wave fashion? So we could actually calculate for something, a piece of matter, substance, what its wavelength would be if it were moving. Now, if you actually calculate this, like I said, I'm not going to make you calculate these. If you did this for a baseball, okay, you would get that the de Broglie wavelength is 1 × 10⁻34 meters. Like that's how much it's like moving. That's so small. Like that's not even on our electromagnetic spectrum. So like this, it doesn't really apply to large things. Okay. So size matters. It really only applies to really small things like electrons, because if you calculate the de Broglie wavelength of an electron, you get like 80.8 meters. It's a much more acceptable answer, something that we can actually wrap our heads around and would be on the electromagnetic spectrum. So electrons act differently. Again, you don't have to calculate these. I don't know if you want to write that down. Don't need to calculate. Okay, but we're getting into how electrons can also kind of act like light. Okay, they can act like waves, they can act like particles. They did actually prove this more recently when you shoot electrons through things, or like photoelectron microscopes, things like that. Electrons can kind of act like waves a little bit. So this brings us to the more recent discoveries having to do with quantum mechanics. So the Heisenberg uncertainty principle. Not right now, in a little bit. I already had some. Oh, I see that. Goodness gracious. Okay, so the Heisenberg uncertainty principle is something you might have heard of before. It has a little bit to do with Schrodinger's cat, and it's that we can't know both velocity and position of electrons at one time. So that's something to think about. Now, if I'm going to compare like how a bullet moves to how an electron moves. So bullet movement is governed by physics. Okay, this is all physics. Okay, it has to do with motion and velocity and position and any forces acting on the bullet, right? So like gravitational force applies to a bullet. It's eventually going to hit the ground, right? How fast it goes, it's going to slow down because it's hitting those air particles. That we can describe how a bullet moves in physics. Now, electrons are a little bit different because they are so small. A lot of those forces and things actually don't apply to them. So what we started doing is we try to measure how fast these electrons are moving, or we try to measure where they are. And those are so small, there's actually a limit to how precise those measurements can be. So Heisenberg actually came up with this. Again, this is an equation you don't have to use, but essentially it gets us to the fact that while there's always an uncertainty in measurement, when you're measuring things that small, the uncertainty is so large that we actually can't really make specific claims. So very small measurements have high uncertainty. Okay, we can't actually know a lot of things for that many small particles and what they're doing. So again, you would not have to calculate these. So I'm not gonna have you calculate these. The whole idea is that an electron and its velocity, there's a very high uncertainty for how small things are moving. So the takeaway is there is a lot of uncertainty for small particles when we're trying to measure where they are or how fast they're going and things. There's a lot of uncertainty in that. And the more that you know about how fast it's going, the less that we know about where it is. And that's where actually like Schrodinger's equation comes in. And like I said, this is a lot of PChem stuff. So if you're super interested in this, you might want to go on to take some PChem classes. And that gets really interesting. So this brings us to a couple of other aspects of the Heisenberg uncertainty principle. And that is that larger things, larger particles, we can determine their velocity, their position, their forces on it, and all of that. So for larger particles, they have a determined, like we can actually measure with a low degree of uncertainty, velocity, position, and their forces that are acting on it. Okay. When we're talking about electrons, these are indeterminate, or there's indeterminacy. And that's that we cannot know. This is the main aspect. Hang on, this is the main aspect of the Heisenberg uncertainty principle. We cannot know both the position and velocity of an electron, which we can't. They're so small. The uncertainty brings us to, if you think you know one, you know nothing about the other. So we cannot know both of an electron, which means we can't predict its path, cannot predict its path. Okay, so oh yeah, what was your question?
Is this inability or indeterminacy, is this a result of instrumentation, or is this having to do specifically with the math?
So that is a great question. Part of it has to do with the fact that, yeah, we can't measure that small. But mathematically speaking, the probability of knowing exactly this is so low, we can't mathematically determine it. So this really does have a lot to do with calculus and using quantum mechanics and quantum computers, and that we physically cannot figure out both.
Okay.
So yeah, that's a fantastic question. So there's an equation, and it's the Heisenberg and Schrodinger equation. And like, if you know more about this part, so the position, then the probability of knowing the velocity like decreases. And if one increases, the other decreases. So we can never really know both. Okay. Which is why we don't actually know where electrons are and where they're moving. We know that they don't go in circles. We just know a probability of where they are most likely at. And that is what we're going to talk about now, because when you look at an atom and we're like, oh, well, the electron is here. Well, it's somewhere in this general region, most likely. Is it actually truthfully what we're saying? So that's essentially what the Heisenberg uncertainty principle says. We can know, it's like, this is how a bullet moves. This is how an electron moves. So if you're looking at this picture here, it's actually a distribution of probability. So like I said, this has a whole lot to do with math. All these dots represent a place where the electron could be based on calculation or observation. Maybe we've plotted the points of electrons at certain times for certain elements for a long period of time. You actually get this distribution map. So the electron is one of these dots. It's somewhere in there, probably. But we don't know for sure. So electrons move with this indeterminacy. We mathematically can't figure it out. And so like, this is a normal particle, like a bullet or something. I'm gonna write bullet. Electrons, on the other hand, we can make a distribution map of where they probably are. So we actually have all of these fun numbers that describe where an electron is, which is what we are going to talk about now. Okay, So quantum mechanics, hang on, I'll leave that up there for a minute. Quantum mechanics and atomic orbitals. So we're like looking at these electrons and we're like, oh, it's somewhere in here. Well, they actually have general shapes. We can mathematically determine the shape of this area where the electron is going to be. This is where Schrodinger comes in. Schrodinger's cat, both dead and alive at the same time, in case you don't know what I'm referencing. It's like, well, we can't know the velocity and the position, because if you check the velocity, then we know nothing about the position and so on and so forth. So it's a lot more complicated than that, but mathematically speaking, we can't know about